Okay, so it's 3, so let's get started. Start a little bit late because of the tests. Right. So good. So I'm glad to see some people managed to turn in their projects and still stumble into class. So that's good. If you didn't see, I posted on Canvas this morning after getting some questions about it. If you turned in a reasonably final version of your project report and you want to polish it a little bit, you can do so up until midnight with no extra penalty. You need to have something by now should have been turned in that could have been a final report, 80% the way there at least, for it not to count as late. But if you want to polish it a little bit more, then okay, that's fine. I think that's better for everyone, especially me. So that works. Other thing is on Monday, the poster is due. So there's a lot of stuff, like I wrote a bunch of stuff about how to do the posters in the project document, so please look at that. Kind of just a couple things to point out, highlight. There are two main types of posters in the world. So there's A and B here. Where A is meant to be kind of standalone. You put them up on a wall, and you don't need someone there to have the poster be effective. Often these have a ton of text, and people will go up there and they'll read like a paragraph on there. The other type is one where they're meant for you to stand next to it and explain what's going on. And really, they're meant to be an aid for your explanation. They're not meant to be standalone. You want to explain something, you wish you had an equation, you wish you had a figure or a chart that you could point to while you're explaining it. That's type B. These posters should be type B, okay? So don't make too much text on there. Just kind of make the big things as an aid for presentation. Right, so, focus around, build it around the charts, right, in the illustrations. Okay, so then there are lots of ways to make these posters. One is, if you're really nervous about this for some reason, but you should be fine, but the way which is acceptable, which is okay, is just to make like 8 or 12 slides and then print them out and then put them on up together. If you want to do that, that's fine. It's not going to look as good, but it works. You get your idea across. The better way is to create one big image, and in that case, we'll print it for you. Okay, there are lots of programs you can use to make it, like PowerPoint or Keynote. Just make one slide the right dimensions and put everything in that one slide. And then you can, if it's the right dimensions but not scaled, we'll scale it up when we print it. Okay, so don't worry too much about that. And the more fun, the more wild, the better. There's going to be a voting by your peers of who has the best posters, and you can get some bonus points for having really cool posters. So hopefully this is a fun aspect now that you finish with the report. Now you can actually do something even more fun of a little artistic side. There have been some really, really cool posters in the past. So someone did like text analysis and made it look like the whole poster was a newspaper or something like that. I don't know, but there's lots of crazy fun stuff you can do. I hesitate to show you other posters because the best ones are the ones that don't look like other posters I've seen before. So go in and kind of go wild, but remember not to put too much text on the poster. Avoid full sentences, stuff like that, and have the title and the names match that of the project report. Okay, that'll also be important. Okay, so finally, there's a version of them due on Monday, and then we'll try and very quickly give you some feedback and maybe ask you to make some changes if they're very far from what we were hoping they would be. And then I think I'll work this up. I'll work this up at the end of the week, but I think by next week, Wednesday, you'll send the final version to Chris Coleman, who works in the CS main office, and he will print all the posters for us. If you're doing the beginner slides type, you can go print those on your own. But if you want to make one big image, we'll print it. It'll be 2 feet by 3 feet or 3 feet by 2 feet. Either way, so either orientation is fine. You could make it 45 degrees as well if you wanted to. Yeah, we'll print the PDF you give us, and then it's up to you to figure out how to hang it. And so, yeah, so we'll and I'll put up details exactly in this document, and I'll post on Canvas about the final details about this. This will depend on the date we decide for the actual poster session. Okay, so this morning I posted 2 options for when the poster session would be. One would be which I have scheduled, is the normal exam time for this class, which is May 2nd, I think 3:30 to 5:30. And no one should have any conflicts then, right? Because the exams are scheduled, so if you're in this class, you can't have any conflicts. And so that's a safe date. The other one is April 27th, which is a week from Wednesday. And that corresponds with, it'd be the same day as the senior projects. And so the reason for doing that would be that you'd get a lot of foot traffic from the senior projects. We'd schedule it so it's basically starting as the senior projects are winding down in roughly the same area. Last time this was near the atrium in the upper part of in the upper part of this building, and so it worked really well. It's busy for the seniors' day, but then it's over with. So, if anyone has any objections or they have something else scheduled from like 4 to 6 that day where they absolutely can't make it, or maybe be 4:30 to 6:30. Please let me know. It seems to be on Canvas so far, people seem to like the April 27th date. So just show of hands, anyone like the April 27th date or the May 2nd date? So April 27th, May 2nd. Okay. So it's about even. Okay, so if you'd like the May 2nd date, post so on Canvas, just so I see representative people there as well. Right now, everyone on Canvas has said April 27th. So if that continues, if you have a conflict April 27th, then please let me know, and then I probably will, if there's a good reason, because enough people, more than one person has a conflict, we'll probably move it to May 2nd, just because otherwise it's not going to work. Okay. All right, so discuss that on Canvas, and I'll decide by the end of this week. But that's why the posters are due so early, because we need to give enough lead time for their printing. Okay, and great. Okay, so any questions on posters?
Those of us who have, for instance, I told you ours is animated.
Yeah.
We're allowed to bring a laptop and show
That's right.
that as part of our poster.
Sure. Yes, there are a few groups that want their poster to be, or some aspect to be interactive or animated. That's that's also fine. There'll be some spots that will have outlets, and I'll try and have some tables set up. Last year we had it in kind of the part of web in between where those big classrooms are, and so there are a couple tables to the side, and we kind of had this semi-reserved, and those tables have power behind them, and you can set stuff up there. So that's absolutely fine. That's great as well. Yeah. So you don't need just the poster, but this is a great visual aid for aiding discussion. Okay. great. And feel free to turn in posters earlier too. We'll try and give feedback earlier. You don't need to wait till the last minute, although I know everyone likes waiting till the last minute. Yeah. Okay. So today we'll talk about so Mapreduce and also distributed file systems. Okay, and so and I'd asked this earlier in the class. So how many people had heard of Mapreduce before this class? And how many people took this class because Mapreduce was on the syllabus? Okay, yeah. So in the past, those numbers have been drastically different. I've reduced a lecture on Mapreduce because it's no longer like, you know, in the zeitgeist as a very important, like is the important thing about dealing with big data. So part of this will be this story about Mapreduce and also these special type of distributed file systems which are outliving Mapreduce itself. Okay, so you know this has to do with so big data, and Mapreduce is kind of this system that was created internal to Google, which was very integral in how they handled and dealt with big data. But there's kind of a larger story going on here, and that's that you know, when you think of this big data, I want to kind of mention a couple of, you know, this means different things to different people, and often you brand something big data just to get funding or some recognition for it. But there's actually some truth to some of this. So there's kind of a couple properties of this that we will kind of focus on and that have spurned things like these Mapreduce and these distributed file systems. So one is that the data is actually very big. It's actually enormous. This means that your data is at least in the terabytes or larger than this. Right? So this means that it does not just fit on your laptop. A few of you ran into problems when dealing with data because you said, well, if I manipulate it this way, it's not going to fit on my laptop or not in my memory anymore. But Mapreduce is meant for when it's needed to fit on hundreds or probably thousands of machines. Okay, so this is really, really big data. And so there's data like this inside of these internet companies. They're collecting all sorts of stuff. The National Security Agency probably has data this big. So there are places where you can collect data automatically in some way, and the storage is not going to fit in one machine. You need many, many machines to store this data. And so I'll explain why this motivates what we'll talk about today. The other thing is that the data is pretty static, so that it's not really changing over time much. You've collected data over time, or if it's changing, it's usually so usually the updates are just these updates are just appends, where you're getting new data and you just add this onto your data set. There's not a lot of rewriting of the data. Once something is part of the data set, it's part of the data set. And so this means that we don't necessarily need to go in and change something. We can store it and then it's there, and then we want to play with it from afterwards. And the appends are going to be easier to deal with than actually going and changing each of the pieces of data. You could go and do that usually with these systems, but it's not you often don't have to worry about that, which makes it nice. In certain data structures, if you guys ever get into advanced data structures, and even things like dealing with like a red-black tree, doing deletions are often a lot more tricky than they seem to be at first. And in this case, often you don't have to deal with deletions, only appending data. Okay, and so there's been this, part of this, and because of this data, has been what you could call like the data science revolution. And this is kind of a way of thinking about how this enormous data has changed how we do science in general. So I sometimes give these overview talks, and I'll start it with this story about how classic science. So if you've learned in high school, you learn about like the scientific paradigm, right? Who remembers what the scientific paradigm is? Observation, hypothesis, experimentation. Yeah, good. So I like to write it a little bit differently. So maybe you start with observe, but then somehow the first step here is the hypothesis. You somehow think in your head, you think of this hypothesis about the world. And then there's the experimentation, but often what this means in terms of, from a data point of view, is then you go and you and gather the data. So once you have the hypothesis, you then go and gather this data. And then once you have the data, you you draw some conclusion. And so in order to draw this conclusion, you often run statistics. Too many T's in there, stat. All right, so you run some statistics in order to draw these conclusions. Okay, and like this goes back, 100, 150 years, and until the last decade or so, most science was done in some manner like this. And the fact that you make the hypothesis and then gather data is often essential for the real fundamental hypotheses within the statistics, for those to work. There's some assumptions that this data is not correlated with other things. This is drawn specifically for the statistics you're generating. And so you would calculate some statistics and then draw some conclusions. And it could be that your hypothesis was wrong and you go back, right? And you make a new observation, maybe based on this conclusion, make a new hypothesis and start this over again. But then when you do it over again, you should, in principle, gather more data, right? And so there's some kind of flexibility with that people often do with this, but this is the classic paradigm. The data science paradigm usually starts by saying you have some enormous data that you started with that has been just collected. Maybe you've done this a bunch of times and you keep pouring this gathered data down to this data set that you just kept around, these log notebooks and so forth. Or maybe you're an internet company that is, or Google, the goal is to just gather and organize the world's information. At some point, they had a few mottos, don't be evil. The second one, I think, was gather and organize the world's information, right? And so that was, for like a long time after they built their search engine, that's what they were doing. They were just trying to figure out how to do the information. They figured profits and other stuff would follow, and that was true. There are these things like the Sloan Digital Sky Survey, where the point, this used to be astronomy was, follow this thing, that someone would make a hypothesis, they'd go and they'd request time to observe a specific part of the galaxy with the telescope. They'd wait weeks or months to get a chance to observe it, and then based on what they saw, they would decide whether their hypothesis was correct or not. And they often would not share the data, because it took them so long to wait to get in line with the telescope. So the Sloan Digital Sky Survey said, well, let's just go and get funding to have one telescope dedicated just to collecting data, and then we'll share it with everyone. Right? There's also like the Human Genome Project, right? The goal is, instead of testing individual people for diseases, we would try and put together an example of the whole human genome and then make a base of this and make this public, and this would kind of spur science. And so you started with these enormous data sets, started around 2000 or so, and once you do this, then the step is you try and do some data mining on this data, and then this, so to draw some conclusions. Right, so you're still trying to draw the same sort of conclusions, scientific conclusions, but you've kind of replaced the hypothesis and the statistics together in data mining. It's supposed to be what this class is about, I guess, right? Now, there are certain issues with how this interacts with classical statistics, and these are not completely resolved yet. But you're starting with this data, and then you're trying to essentially form a hypothesis while checking whether it's significant at the same time, right? And so this is kind of this new view of data science. Okay, this was supposed to be about Mapreduce. Okay, so how does Mapreduce fit in here? Well, Google, for instance, had all of this data, this enormous data, and they wanted all of their engineers to quickly be able to access it, but it was so big it was a pain to use. If you have the entire web graph, or you have all of the text from all of the web pages, how do you, and you have hundreds of engineers, how do you let them all experiment with it, try and create new products with it? It takes so much time to work with these big data sets. They don't fit on one machine. Remember, these needs to fit across many different machines. So how do you make this accessible? And so, at the time, there's these classic database engines. If you take the 5,000 level database systems class, you'll learn all about these. And these were designed around these highly structured data that often fit on one machine. Yes, there are some extensions that are parallelizable, but that's not the thought process. The thought process was to take this very structured data and find out how to parallelize it, where these distributed file systems, so these distributed file systems were thought from the start of flexibility and parallelism about them, right? So before Mapreduce, and I think this will be more of a lasting kind of thing, is these distributed file systems that were based on these key value pairs. So in a traditional database, you would have tables where every object has ID and then a bunch of attributes. Here you have these key value pairs. And so you're going to store these, and these are, because they're not structured, they can allow for different sorts of data to fit in the same one big system. Okay, so these distributed file systems, these key value pairs could be things where the key is going to be some sort of ID. Let me have some examples here. So the key could be something like a log ID, and then the value is the actual log, right? So if you're running a system, it occasionally spits out error messages or these log messages, and this big log table is going to be like this. So it just has a ID describing, and then whatever you want in the log. It can be processed and scanned and looked for certain elements later. You can put more structure within the value part. That's very flexible. It could be that the key is like a web address, and then the value would be the HTML. Or if you're just building like the web graph, you might just want the outgoing links, right? So if you just care about creating doing PageRank, then for every web page, which has a unique ID, its key is web address, then you have the outgoing links to other web pages, right? So then that would be what's in the value. Or if you wanted to process it for building an inverted index, then the HTML somehow just made a text from that contains all the information you would need. Or if you have a document ID, say you have a corpus of documents, there are these collections of these news articles, for instance, you may have come across, then then the value might be just a list of words inside there. Maybe you're using the bagged words model, maybe it's just the text in the documents, right? Or you could flip this around. You could have that the key is the word, and then the value is something like the list of the documents that is containing the word. Okay, so I have a list of all the documents which contain this word. So this essentially is the inverted index to some extent, right? If this is a search query, then if I find this key in my database, then this is the list of documents or the list of web pages which contain this word. So you can think of these as these key value pairs. Yeah?
I have a question about distributed file systems. Is this like, you say like, is it like a different type, is it basically like a NoSQL database you're talking about here, or are you talking about like, just like you have all these files and the keys or like the names of the files, or does it really matter?
Right, yeah, so some of these, NoSQL databases are kind of, usually have even more structure on them than this, but that's the right thing to think about. This is like these NoSQL databases. Yeah. Yeah, so that's right, but you can think of this more generally, more flexibly. So we're in this, for here, we're just going to say, okay, it's just the key value pair. Okay, and so now these, and so I'll talk a little bit about how this is stored in a second, but there's kind of some kind of evolution here. There's some stuff that came before this, but what we'll talk about, there was this Google file system, and then sitting on top of this was Mapreduce, and this was inside of Google, and then there's this open source version, the Hadoop file system, which then Hadoop was sitting on top, and these are open source versions of the Google file system and Mapreduce correspondingly. They weren't quite the same. And because the Google file system was internal, this was kind of the first view of it, and so this part was inside of Google, and it was talked about in some research papers, but people didn't have access to this, and this took maybe 5 years or more later to actually be developed in a stable form. So this was talked about even in research community, and people tried to study it before this was actually stable. What's happened since then is that there's been a lot of other stuff that's been built on top of HDFS, most notably the Spark system, which operates, basically has the same sort of processing goals and behavior as MapReduce and also Hadoop. And it's kind of as replacing them. There's a little bit more complication in getting stuff to work into implementing it, but it's going to be much more efficient, and we'll discuss why that is. There's some structural difference between Spark and Hadoop and MapReduce. And so this is one prominent thing, but there's a whole other ecosystem of these other tools which sit on top of here. There's something called Pig, which is supposed to, I'm getting this right, which is, yeah, so Pig I think is the SQL, it's kind of a way you can query HDFS in a way that looks like SQL. And it's a horrible mismatch. The data's not organized, so the same things that would be efficient in a traditional SQL database would be efficient here, but you can write them anyways. And so these tend to be can be really, really slow, but people are familiar with SQL, so they wanted this. So they built it, and then they're like, oh, why is this so slow? And hopefully you'll realize through this lecture why that's going to be the case. But there's a whole bunch of these other tools built on top of the HDFS. And so kind of Hadoop is kind of not being used as much as being replaced by Spark and some more specialized things. There's a variant that sits on top that does some stuff with graphs, especially for graphs, and that you could have done that within Hadoop, and people tried to do that, and they said, well, I can write it's a slightly different interface for a lot of graph-based things, and those are going to work more efficiently than Hadoop. So this is kind of not being used much anymore, and I've heard Mapreduce is being phased out, or mainly is phased out within inside of Google. It has more specialized tools for certain tasks. But again, we'll talk about within these systems because they kind of give a general overview of what can be done, and then you can imagine specializing these for certain sorts of more specialized tasks you might want to do. That would also be common. Yeah?
So I always saw Mapreduce as more of a concept than a system, but here it's more like a system.
It's, yes, so it's both. It's a system that people have studied and as a concept because they didn't have access to it. And so the concept of Mapreduce is the same inside of Hadoop. And it's almost the same as inside Spark, except for one or two very critical differences. And that there's these things that are inspired by Mapreduce. There are these graph-based libraries and things for dealing with logs better in specialized ways that are inspired by Mapreduce. There's been some computational models, a way of thinking, like how we talked about streaming algorithms. It's a different way of thinking about how efficient an algorithm is. People have looked at that for the concept of Mapreduce and tried to formalize this. I taught a class a few years ago, where we looked at some of these algorithms, but there's like a bottleneck in its round complexity of Mapreduce, which seemed artificial to me 5 years ago, and now, I mean, I'm not the only one, but now Spark has basically gotten rid of most of that overhead. So the things that were most important in Mapreduce and Hadoop are no longer as important in the model. So this model itself, in some ways, is still around. In some ways, it's changed dramatically. What has stuck around a lot more is this HDFS, and I'll talk a bit more about that. Yeah, so part of it is this key-value pair, which has influenced these NoSQL databases as well. They're built with more structure on top of this. But the other thing is how the data is stored. And so, I mean, one way you could think of it as you just have this one file, right, that this is, you know, is terabytes, right, terabytes of data, and it just has a key and a value, key, value. You just have this whole file down here filled with this, and you think, okay, I need to store this file, and I need lots and lots of space to do this, right? But you don't just want to think of it this way. What you actually want to do is to break this up into these blocks. Into some blocks of data, and usually they're not too small, like you would think of it like a cache, but they're like 64 megabytes each block. Okay? And then you're going to think of storing all of these blocks separately. And they're filled with key value pairs. Okay? And so what starts to get interesting is that you think of now having these different machines. Call this M1, M2, let's say M3 up to, let's call this ML, right? So you have all these L different machines, and this, remember, this is like hundreds or thousands of machines like that, right? And so what you would do is you would put, for each block, so you would have B1, B2, Bn. Okay, and so you'd put B1 across, you would replicate it on a few different machines. So each BI you would put roughly 2 or 3 copies. Okay, and then if you look at block B2, which might be right next to it in the ordering, so then if I look at this block B2, maybe on 1 it's right next to it, but then it's here, and then it's on this other location here. So they're on the same machine here, but then they're otherwise not on the same machine. There's not locality between these blocks. So no locality. So traditionally, if you think about data structures, often the key to a data structure is to put data locally next to each other, so that things that you would need to work with each other, you would put next to each other, so it's easy to do comparisons, like if you sort something, or to look stuff up for range searching. We talked about these hierarchical range trees, and you organize them hierarchically and spatially, things that are next to each other in the same part of the tree. Here you're doing the opposite of that. You're making them non-local, right? I'm putting blocks that are right next to each other in the ordering. So this was, say this was B2, and this was B1. I don't necessarily put them next to each other on machines. In fact, this is often done at random, right? So you put each block, you replicate it 2 or 3 times, and then you randomly put it on each machine. Okay, and so this is how the data is stored. So you have this huge file, you break it up these blocks of 64 megabytes, so not a huge size. You replicate each block 2 or 3 times, and hard drives are cheap, right? So even though it's terabytes, you're willing to go to 2 or 3 times as big, because at least Google hard drives are such a small expense of their total operation. And then so they replicate it 2 or 3 times, and then they don't store things locally. Okay? So why does this structure make sense? Why is this? What are the advantages of having these blocks stored with copies and not in the same location?
Same speed?
Yeah, so let's say. So one is going to be redundancy. So why? So speed, yeah, so we'll talk about speed is more complicated. And actually speed is not usually the goal here. They're like, it's gonna be faster than reading all of the data set one by one, but they're more focused on scalability, and we'll get back to that. But why is redundancy important?
Disk failure.
Yeah, so okay, so how many, let's see, maybe there are like 30 people, 20, 30 people here today. How many people have had a machine crash in the last year? Okay. Oh boy, that's had some bad luck in this class. Okay, so about 5 people. So so maybe that's 20% in the last year. Now let's say that, let's say instead of having 25 machines, there are 1,000 or 10,000 machines, and your data is stored on all of them, right? And so if in the last year, then let's say it happens once, so let's say that was 20% of people, that means roughly every 70 days of a machine's runtime, it crashes, right? And so that means if you have 1,000 machines, that you would expect one to crash every 70 days, but that means that, well, you have way more than 70 machines, right? You have, let's say it was 700 machines, so that means you would expect 10 of those to crash every day. And that means one to crash every 2 or 3 hours. That's probably a little pessimistic. Most of you probably have laptops where laptops get dropped. Data center computers probably don't get dropped as much. But they still crash. right? And so it's a common occurrence when you scale up data to this many machines that you're going to have these crashes, and you don't want to have to restart everything when that happens. So if you're trying to process something over all this data set, and the first machine fails, and you were using block 1 and block 2 on this machine, well, what you can do is you can then look up block 1 on machine 3 and block 2 on machine 2, and you have this redundancy here. Okay, so it's already built in. You don't have to wait for that machine to be actually rebooted. The data centers are so big, what they typically do is they cycle through them, and it takes 1 day to do this, and for all the machines that have gone down in the last day, they reboot them. So this machine may be down for a day, and they're like, that's fine, we have backups. Right? So they'll actually probably, when they know the machine is down, they'll actually replicate these on another machine, so they try and have 3 active copies. And so then also, because these are not on the same machine, because this one went down, you may have finished processing what you did on the other machines. When you realize this is down, you don't have to wait for this machine 2 to have the exact same stuff. You could then say, well, do what I need in block 2 on this machine, and do what I need in block 1 on this machine. I can do them in parallel now. And that was because I didn't store them with the same, I didn't store the whole machine identical to another one. I did this based on blocks. Okay, so the fact that I spread this out makes this failure much easier to recover from and much faster to recover from. Yeah, so what else do I want to say? So the other thing is that, so heterogeneity, that's a big word that I may have spelled right, depending on my penmanship. I can do a lot of different things with this format. As long as it fits within, the data within a block is enough to capture a few keys. I can do this with most sorts of data. All these different examples I did before, I can break down in blocks. I can do it in this way. The format is very flexible. But also when you have a query, what you want is that the computation is carried out in parallel. And so if your data is all stored, say all my data was stored on machine 1 that was relevant to some process. Well, then the first thing I need to do is either I need to run it all with machine 1, or to do it in parallel, I need to send all the data across to other machines to do the parallelization for me. Now, if I start looking at it, I can say, well, I can run on machine 2 and machine 3 at the same time because the data is already spread out across different machines. So the parallelism it's already set up to run in parallel. Yeah.
Are these just file servers or are these computation machines as well?
So they're both, right? So the idea is you can bring the computation actually to the data instead of bringing the data to the computation. The cost of transferring the blocks across machines is a pretty sizable, and you'd want to avoid that if you can. Right? And so the data is going to be in this format, but fairly permanent on these machines. The machines go down every so often, but each machine, it can be easily a year before it goes down. And so you don't need to update the data on each machine. Right? If you're just appending new data, you can spread those across different machines, but most of the data is static. So they're sitting there, and now a lot of different engineers can ask queries of the system, and when the machine is free from the other queries, it can run this. It doesn't have to move the data to do so. The data is kind of static there. They've captured the whole web. They have all the logs of their whole search. All the search logs are stored across this way. And what page people linked on, all that. It's sitting there and they can ask these queries, and the parallelism is already built in. Okay, so this is kind of this principle of this very parallel distributed file system. It's very flexible. and it's redundant because the disk failure, and this redundancy breeds resiliency. So when the disk fails, the whole system doesn't have to stop. There's this other view of parallel systems that's often people work in these high-performance computing systems where they also deal with large-scale parallelism. And it's much more care is to keeping into allowing the machines to stay up for a long period of time, that the code is very robust. But if one machine crashes, they often have to restart a lot of what they've done. They'll do some stuff with some checkpointing so they can try and recover partway through the operation, but this becomes kind of a big pain to do in a lot of those systems. And so this is the opposite, saying if it fails, I can keep going. And because I can make it much more parallel across different machines, I don't need each machine to be as fast. And so, there's a lot of cost in between transferring data, but often I want to avoid transferring the data, or I just am going to do it at one step, and this will be Mapreduce, which we'll talk about next. If I have just more machines, then I have to process less data per machine, right? I can scale this out very far. I can make this very scalable across many, many more machines, and it doesn't really slow things down. So it's easier to buy more cheap machines than fewer really fast machines. And so at the time when this was coming out, they showed the breakdown of like one really fast, machine that had like maybe many cores within it versus a bunch of each cheap machines. And the total amount of computational power with very cheap machines you can get for the price is much, much more. And so this kind of went into it, but I think this is no longer it's still a big cost at Google, but not as much as I think just paying the engineers is pretty expensive. Actually, I'm not sure what are the big costs of these companies, but it's very small compared to the profits that they just pull in. So, okay, so this is the system, and this, as I mentioned, this is kind of this process of storing this huge data is outliving Mapreduce and Hadoop itself. But let's talk about kind of Mapreduce, and this is essentially the same concept as Hadoop here. Okay, so the idea is that you're going to be sitting on top of this data in this distributed file system, and you're going to access it in a few fairly simple ways. And then all the stuff with dealing with the parallelism is going to go on behind the scenes. Okay, and so you're going to do these you can kind of think of it as these 3 steps. And you actually, the first step is called map. There's kind of a 1.5 step that's called combine, which is optional. There's a step called shuffle, and then there's reduce. Okay, and so as a programmer, you would just write what's in reduce and what's in map. Shuffle is done by the system. Okay, so map is so let's break these down. This operates on the data in the distributed file system. Okay, so what it's doing is going to read the key value pairs in each block by block, and it's going to somehow process these key value pairs. So it's essentially mapping. So there's going to be some map operation, which is going to take in one key value pair, and is going to output another key value pair. Okay, it's going to be the same basic format, but what the key means and what the value means could be different, and I'll go through a bunch of examples of this. It could be the key is the document is a web page, and the value is, or the key is the web address, the value is the actual text on the web page, And then here, the key is one word that is found on the web page, and the value is the link to the web page. So this might actually be a set of these key value pairs. So it's going to read each of these, and it's going to output potentially a set of key value pairs. So what the shuffle is going to do is it's going to the shuffle is going to put all key value pairs such that they have the same key on same machine. So this is where the data is moved. This is where the data is moved in between machines. So it's going to output a bunch of key value pairs from the map step. This is done on parallel across all machines. And then it's got a bunch of these key value pairs, and all the ones with the same key are somehow going to get moved on the same machine. Hopefully in the same block, if possible. But they could be in consecutive blocks in the same machine. They might be coming into this machine in a stream. There are a few different ways to think about this, and then this reduce step is going to essentially get a key and then a bunch of these values. And it's going to output a set of these key value pairs. Okay, so what this does is it put all the key value pairs with the same key on the same machine. The reduce step then says, okay, for each key I see, I'm going to get a list of these values. And it's going to somehow, all of this is now going to be sufficiently local. So it started that everything was non-local. Then the mapping tells you how to localize it. The shuffling, which goes on behind the scenes, actually moves the data. And then the reduce step now has stuff localized by this key value. And then you can process all of these values together to get some new key value pairs. So every intermediate step, you think of it in these key value pairs. And so these are the three steps. And as a programmer, this always happens. So you know it's kind of combined based on the keys. So your job is to write this map operation and this reduce operation. And they're often very, very simple, just a few lines of code, each of these. The hard thing is parallelizing this across all machines. If one machine fails, you know you have to go get the data from someplace else. And all of that is the system, Mapreduce or Hadoop, that handles this behind the scenes. And it does the movement of this data, and if one machine becomes slow, then it's taking too long, it'll send the data elsewhere. So what might happen is you might get some key that has a ton of values, and you don't want anything else. The machine that has to process these, you don't want to have to process anything else. So you would send those other similar keys, other keys you don't want to wind up on the same machine, and the Mapreduce system, Hadoop, should take care of that behind the scenes for you. There are certain things that will be hard to avoid, and you need to think of kind of from an algorithm design perspective to make sure those are efficient. Okay, and then this combine phase here, this is basically reduce before shuffle. Okay, so when you do this combine, this map can output this set of key value pairs, which are all in the same machine. This shuffle is when the data is moved. Sometimes these are repetitive. And so you don't want to send all these across the network if you don't have to, so you can combine them before you send them across the network. So often you're going to redo the reduce step locally before you shuffle it. And that's what the combiner phase is. Okay, so let's go through some examples, and then I'll talk about a few issues kind of as we go. Okay, so the simplest example in Mapreduce, which is like the hello world of Mapreduce, is the word count. So if you look this up online, for example, this is going to be the first thing that you find. There's a reason it's like that. You just want to, it's a really good first example. Okay, so what you have as your input is going to be a large set of some documents, and so each of the documents you're going to think of as a set of words, and so for the output, what you want is for each word, how many times does that word occur? So the count of that word. Okay, so if you're looking at the word apple, how many times does the word apple occur in this huge document, right? So think of all of Wikipedia. Okay, so how would you write? So now we just need to write these map and reduce steps, right? So we have these documents, which is just the document. The key it's not so meaningful, but we just have this list of words. How do we write these map and reduce steps? Yeah.
For each document, like go through and count each word and then like tally up for the document. Or
yeah. So what we're going to get is the input. Essentially, the value is just going to be word 1, word 2, word 3, word n, right? And the map phase is just going to convert this into word 1 and a count 1. So the value now is going to be a count, word 2, and then I see it once, I count it, right? So the advantage of this thing, where I'm thinking of, I'm doing something very simple. I'm just reading through this document. I process it through memory once. Every word, I turn it into this key value pair form. Okay? Very, very simple. And this reduce step, so now once I have all these words and a count of 1 next to them, this reduce step is going to get some key, which is the word, and so it's also going to get a bunch of these values. Right, so it's going to get, for one key, the shuffle phase will put all the same words on the same machine. The reducer will be able to see, for this word, bird is the word maybe, then a 1 for every time it occurs. And so then the output here is just going to be the word is the key, and then here is just going to be 1 to k of vi. So I'm just going to sum up all of the counts. So I'm just going to write a sum of these things, right? This is word count. Very simple.
What's the map has an input that's a key value, right?
Correct.
What's the key?
The key here is it's the document. You have a set of these. It's the name of the Wikipedia article. Turns out it's not going to be important. So you just care about the values here. And often the initial setting may be, you may have many things stored on this distributed file system, basically the key says, if this is a Wikipedia article, so if the key says Wikipedia article, then do this. If the key is all the HTML links out of a web page, then ignore it, right? So you only operate on the key value pairs that satisfy the initial criteria. So it's kind of a so often when you think about these, you think about, okay, I only have the data in front of me that I care about, but often on the system, there could be other stuff there that, right? So this is pretty simple. So, you know, it's good because the whole thing is incredibly simple, but at the same point, this will not work. There's some big failure point here. Something horribly wrong is going to happen. Like, it'll work, but it's not going to work as well as you would think it would. What's going to happen if the word equals the?
Blow up.
Yeah. Essentially, it's going to blow up. So this occurs, say, 7% of all words. Okay, and so keep in mind that my data was supposedly so big that I needed thousands of machines to store it. Now, 1/7 of or not 1/7, but 7% of 1,000 is going to be something like 30 machines. But I wanted all this on one machine, so that means my shuffle step is going to send all the words onto this one machine, which then has to process 7% of the data. So I've lost a ton of my parallelism here. Doing this sucks. All right, so this is going to take way too long. Okay, but there's also a simple fix.
Just get machines reducing that.
You do?
Just like split them up in different machines and reduce them.
Yeah, so you could say, well, if this one machine is getting overloaded, I need to send it across different machines. And in general, you could do that. In principle, you shouldn't be able to. The way it's designed, this reduce operation should, it may need to do something global that required all this data to produce an answer. Let's say you're trying to find if a graph is connected. If you're missing one edge, it may no longer be connected. And so it's harder to in general do this. So in practice, you could do that, right? You could say, okay, you would instead, making the key just the word, you would say the word, and then also if it occurred in the first 10% or first 1% of all the documents, then say word, and then an ID for the first 1%, for the second 1%, third. So it has more information in the key, and so then they get sent to say 100 different machines, and then you combine them together. You could do something like that with an extra round. And we'll talk a little bit about rounds. But there's something simpler you can do. And I mean, it's basically in line with what you're saying, but you can have this combiner phase, which sits right here. And so this combiner phase is just the same as, is just going to be the same as the reduce phase. And for each word, it just is combining them the same way that you do on this reducer. So basically it means before you send the data off of the map, off from the original computer it's on in the map phase, before the shuffle phase, you do this reduce step. And then when you're adding up these VIs, if they're not just ones anymore, this still works. And this works because adding is commutative? What is it? It's, I guess, associative, whatever. You can add up subparts and then add them again later. And any sort of operation like this, like doing a union or doing the max, where then you can do a combined phase first, and it will save a lot of communication. So not only will you not have this last reducer be overwhelmed, but the amount of data moved in the shuffle step is also going to be much smaller. And so the bottleneck in the runtime is often either in the shuffle step, if you have to send a lot of stuff, if you didn't design it well, or in this reduce step. So it's not finished until, so there's this notion that happens here that's called the curse of the last reducer. So where you send the data off and there's one reducer, one machine that's trying to reduce, that is taking 100 times longer than all the other ones. And sometimes this happens because the machine got slowed down because some other process, sometimes because you designed it wrong, and the word "the" is 7% of all the words. Right? So if you do this combiner phase, this will help with this. Sometimes you need some algorithmic thinking in order to do this. There's there's nice examples that we won't get into about counting the triangles in a graph. And there's a way to design the algorithm to avoid kind of this curse of last reducer. And it kind of, like, it seems like a very simple difference, but it can really change the algorithm. We won't have time to get into that today. Okay, so 10 minutes left. So let me say a couple things quickly. Let me give another index. So another classic problem is the inverted index. And kind of, there are two main computational things that, as I understood, that were going on inside of Google when Mapreduce became so important. One was doing PageRank, which I have time, I'll quickly sketch. And one was the inverted index. And this was creating this index where for every search word there was a bunch of these relevant web pages. Right? So that's the case here. The input is the web. Right? So I have all these web pages and they have words on them. Right? And I want as the output, I want to have, for every word, I want to have the list of pages which has that word. Right? So for every word, I want to have the list of all the pages that has it, so then I can just read off that list. And maybe I want to sort them by some searching criteria that may involve PageRank or something like that. So with each page, I can also pass along its page. I can like sort these in some way. Okay, so then I'm going to go from, say, the HTML into a set of these. So the container of words, it's going to have a word, and then the page and some other info, which might include the page rank. And it's going to be word 2, and it's going to have the same page and other info in here. Okay, so map step, I just turn the HTML into this other thing. I'm just text processing, and then the reduce step. And so then I can do a combiner on this if the word occurs multiple times. And then maybe in the combiner can also have the number of times the word occurs. That might be helpful. And then in step, I'm going to have a bunch of this page 1, and then page 2, and page 3. Right? And basically the output is going to be almost exactly the same, except I'm going to sort these page 1, page 2, up to page n. And so I'm going to have them in some sorted order so that, and this is maybe the search order. And really all I would really care about maybe is the top 10 or maybe 100 words in this order. But there's some way that I've converted it into this output, which is now my inverted index. Okay, so again, very simple here. Okay, so a couple of things to point out. Mapreduce is really good when the input is a large key value pair, this document with lots of key value pairs, and the output is 2. Okay, if the output is going to be a small value, say as clusters or the single best page, or just the count of how many web pages are there in the web, right? A single value. Mapreduce is maybe not quite this right tool here. There are other tools that live on top of HDFS which can do this a bit better. At some point, Google had a tool they called they called it Dremel for like a drill, I guess, and outside of it was meant for having a small output, where this is meant for a big output. Right? And they're slightly different in how you'd implement it. But again, a lot of the structure and understanding how this works is the same. Okay, so a couple of other things I wanted to mention. I've got a couple more examples in the notes you can look at if you're interested. Is rounds. Okay, so what happens inside of a round of Mapreduce? You basically have all your data and you do some map phase on this data, and it moves it inside, and then you can think of having these other machines that are going to do this reduce, and this shuffle is going to send them to all the right machines so that you can do this reduce. And the output of the reduce is again a key value pair. And so you think, well, I'm just going to plug this back into the map phase and then do another one of these shuffles over here. Right? So you can do these rounds, you can chain these together. Maybe I can't get my final output in one Mapreduce phase. I may want to first map it to some keys, do some computation, then a bad example would be like if you're trying to do Lloyd's algorithm for k-means clustering, what you would do is you would map every data to its center, right? And then for every center would be the key. You would have all the centers that would be on each machine, and you'd map it to the closest centers. You would send all the data points to the reducer, where the key is the center. You would then re-average the center, and then you would repeat this again, so for several steps. Okay, you could kind of think about doing this, and I remember, like 8 years ago, I was looking up for trying to understand this stuff. I was looking for examples of Mapreduce, and someone wrote this example. This is a horrible way to use it. The reason is each round there's a big overhead inside of Mapreduce, and also in Hadoop. And so a lot of the complexity analysis people trying to develop these algorithms was to reduce the number of rounds needed you needed to do something. Why did it take so long to do a round? Well, each round you have this shuffle step, which is very expensive, where you're sending all the data. And you basically, you don't really, the same machine here may not be the same machine here. You're sending all of your data once. Maybe the amount of data goes down each time. There's some, think of hierarchical, so often the data reduces every step, and maybe you think, okay, it should take less and less each shuffle step. But what's really going on is that in between the reduce step and the map step, this goes back to disk and then back out again. Every time it finishes reduce step, it writes the data back to disk. When you read it, you have to bring it into memory off the disk, and you read it. But it writes it back to disk in each step. And this is for the resiliency. If the machine goes down, what's in memory might be lost, but the disk probably is going to be okay. And so they're really worried about being able to recover this information. And so it kept getting written back to disk, and this takes a long time. Just because it's on the right machine does not mean it's going to be in memory to do another mapping round. Even though in principle you would think this could be possible. But this really causes a big slowdown here. And so the big advantage in Spark is that it's kept the same resiliency but avoided writing back to disk. In order to do this, it does something where it kind of is able to keep track of what happened in the previous map steps, and if something crashes, it just recomputes it in a quick way, in an intelligent way. It figures out what would have been lost, and it stores it in a way that it can easily be recomputed, and it doesn't send stuff back to disk in between rounds. It'll do this in the background, so that it has some robustness properties, but it doesn't do this. It doesn't wait for it to go to disk and then back again in between rounds. And this makes things like running Lloyd's algorithm or other kind of iterative things that are very common in machine learning, it makes them feasible within such a system like this. Okay. So this round overhead was like a really big deal for a while, and now with Spark it's not a big deal, but you have to be a little bit, you have to specify some data structures called these RDDs inside of this in order to make this work. Sometimes, so some stuff that sits on top of those so you can be oblivious to it, but to develop cool stuff, you need to develop these resilient, what are they called? I forget what this RDD stands for, but there's these certain type of data structures that allow you to quickly recover some stuff on crash. Okay, so if you see Spark, this is the big difference. It's not writing back to disk, so the round complexity is greatly improved, but it's built on the same system. Okay, so I have 2 minutes left. Let me just really quickly sketch doing PageRank on Mapreduce. So the key step in PageRank, you actually want to do rounds. You want to do like 50 rounds of the step where you're doing QI plus 1 is going to be equal to, or maybe this was 1 minus beta, this probability transition matrix times beta times this basically is this Q all ones matrix, which is basically just a 1 over n for every step times QI. Right? So you basically want to keep iterating this step, and you want to do 50 rounds of this. And each round of this is going to be one map and reduce phase. Okay, and so what's stable, this is in the probability transition matrix is going to be in the distributed file system, and what's passed in is going to be this QI matrix. And you're going to iterate this process. Okay, and so basically this what the basic idea is to take this P matrix, and then you're going to, the simple idea is to stripe this P matrix, M1, M2, M3, up to Mn, and then you're going to, similarly, you're going to hit this with Q, which you can think of living here, this would be Qi, and each part of Q, part of it only affects this part of the P matrix, and that's going to map over to this entire thing. Right? So what you're going to do is so you're going to store each of these stripes of P. Each column is a web page and has like an average 20 links to it. Right? So I can store a bunch of web pages on each HDFS block, and so then the map is going to take. I'll call this, is going to do something like, let's call this R, is going to get, is going to calculate this RI, which is going to be MI, QI, the, J, RJ, MJ, QI, J. So this part here is going to be QIJ. You're going to multiply this together, get this RJ, and then this reduce is going to just sum up QI plus 1 is going to be the sum over J of RJ times 1 minus beta plus beta over n. Right, so this is dealing with the teleportation. This is done inside the reduce step. The map step is just multiplying this part of the Q matrix times this stripe of this whole matrix, which you can store in. And so there's a way to encode this carefully, and I worked through an example in the notes of how to encode this in these key value pairs. And because this is really sparse, even though this is really big, each row should not be too big, so you can store a bunch of these together. And there's a way you can encode it in the key value pair so that the consecutive things are going to be next to each other inside of the block. And you can do these together. And so you can then multiply these pieces, and you're going to get a bunch of these Rj's, and the sum of them is going to be this Qij. That's going to work if you're not doing the teleportation, but you're going to have this other beta over n term, which is essentially teleporting beta percent of the time. So it would be like 0.15 divided by n, and that distributes that part of the mass randomly every second. Okay, and so you can do the reduce step this way. There's some issues. Sometimes some parts of this are going to be really heavy again, like the word the is going to occur a lot. And so that's going to cause some of these columns to be much heavier, and to get around that, sometimes you want to do these blocks instead. So you want to break it down into this way, and then you have some replication of this part on each of the nodes, but this kind of takes care of these really large cases a bit better, like the word the occurring. But that occurs on the map side instead of on the reduce side. But so this, structuring it this way can have some more advantages and deals, and with the sparsity of your data, this will help a little bit more. And so these are the two main ways to do it, and this comes up a lot if you're dealing matrix multiplication in a HPC style setting as well. Again, they use similar sort of, these are the two main ideas, these blocking and the striping of the matrix. And that allow you to do these matrix vector multiplications still somewhat scalable and efficient. So, all right, so hopefully projects went well, and have fun making the posters. Feel free to send me examples if you're not sure if it's going well, and I can give you some feedback before the formal feedback.